The title is pretty self-explanatory. I'm just going to be talking about cross products and whatever traces they may have. So just as a little bit of a review, I'm going to tell you what a cross product is first. So we're always going to be dealing with unital C-star algebras A, and we're going to let G be a discrete group acting on it by star automorphisms. And the cross product is a larger C-star algebra that satisfies a few different properties. And I'm going to lie a little bit because these properties are not the case if A is non-unital or G is non-discrete, but it should contain a copy of A, should contain a copy of G as unitaries, let's just call them UG, and the action of G on A should now be inner in this larger C-star algebra. So in other words, G acting on A is just A conjugated by UG. And what should your intuition for cross products be? Well, they are more or less just finite sums of elements of G, so UT, with coefficients in A, so AT. And the multiplication is given by this formula written down here, which just follows from the fact that G embeds as unitaries and the fact that the action's inner. Of course, this isn't quite the whole picture because it's not just finite sums, but rather it contains the finite sums as a dense subset. And to get the whole C-star algebra, you just complete it under some kind of representation. And of course, there's two main options, just like for group C-star algebras. You get a reduced cross product where you complete it under a sort of left regular representation, and a universal cross product, which you completed under as large as possible of a representation. And every other cross product is a quotient of the universal one. Now for traces, well, there's always a little bit of ambiguity for traces, but to us, they're just going to mean tracial states. So a trace on a C-star algebra A is a state that also satisfies tau of AB is tau of BA. And why do we care about traces? Well, here's a theorem that you may or may not have seen before. So if we consider the class of unital, separable, simple, nuclear, finite nuclear dimension C-star algebras that lie in the UCT class, then we can classify these, and the Elliott invariant, which is a bunch of K-theoretic stuff plus traces, is a complete invariant for such C-star algebras. And out of the universal and reduced group C-star algebras, we're only going to be focusing on the universal one. And why is that? Well, there's actually a result of Brighter and Kennedy which says the following. If we let Ra of G be the amenable radical of G, which is just the largest amenable normal subgroup, then any trace on the reduced group C-star algebra just concentrates on the cross product with the amenable radical in the sense that, really this should say sigma right here, but sigma of A lambda tau or A lambda t is always 0 if t is not in the amenable radical. So in other words, as I mentioned, we're just dealing with traces on cross product with the amenable radical, but the amenable radical is, well, amenable. So the reduced cross product and the universal cross product are coincide. So really what this tells us is that more or less any result we get on the universal cross product for the reduced one is just going to involve replacing G with the amenable radical where appropriate. Okay, so what are going to be the sources of traces on cross products? Well, here's a result which only takes 1 or 2 lines to check. If you start with any trace on the universal cross product and you restrict down to A, you get a G invariant trace on A. And conversely, whenever you start with a G invariant trace on A, you can extend it to a trace on the cross product canonically by just composing with the canonical conditional expectation, which what it does is it just sends the element AUT to itself if T is the identity element of your group and 0 otherwise. So given this, well, we can ask 2 questions. If G invariant traces are the only possible source of traces on the cross product, given a fixed G invariant trace, what are all of the extensions? And moreover, given that we can always write down a canonical one, when is this tracial extension unique? So these are the questions we're going to be talking about. Okay, so to get a little bit of an intuition for this problem, I'm going to be talking a little bit about something that's seemingly unrelated, and that's simplicity of cross products. So it's a result of Kennedy and Schaffhauser that for the reduced cross product, I'm lying a little bit here because you also need a minimality assumption on the action. But modulo that, the reduced cross product is simple if and only if every map from the reduced cross product is something called the G-injective envelope of A that satisfies a few properties. So it should be G equivariant, it should be unital and completely positive, and it should satisfy the property that when you stick down to A, you just get the canonical embedding into the injective envelope. So the reduced cross product is simple if and only if all such maps are faithful. And they call such maps pseudo expectations, which is terminology borrowed from Pitts and Zarikian, but they consider something slightly differently. They consider the non-equivariant case. And as I mentioned, IG of A is something called the G-injective envelope of A, and you don't need to worry too much about what it is, but loosely speaking, it's something that contains A and encodes the action of G on A. And our idea is that, okay, these pseudo expectations can be used to characterize simplicity. Is there something that we can replace the G-injective envelope with that lets us classify traces instead? So to answer that question, if we consider a fixed G-invariant trace, and we consider the GNS representation pi tau, well, it's already been known since a few decades ago that the dynamics of G on the GNS von Neumann algebra plays an important role in characterizing which traces you can get on the cross product. So it's a result of Bedos from '93 that under some additional assumptions, so for example, if A is simple and the action of G on the GNS von Neumann algebra is properly outer, then the reduced cross product has a unique trace. Also, I should be saying that A has a unique trace tau in this case. But anyways, I should explain a little bit, what does properly outer mean exactly? Well, remember that outer just means not inner. So properly outer should be some kind of really strongly not inner. So here's the definition. We'll say that an automorphism on a von Neumann algebra M is properly outer if you cannot decompose your von Neumann algebra and your automorphism as a direct sum where one of the non-trivial components is inner. And a group acting on a von Neumann algebra where the action itself is called properly outer if for every non-trivial element in your group, that element acts properly outer. And there's one more characterization of properly outer that we're going to be making a bit of use of, and that's the following, that an automorphism is properly outer if and only if whenever X is some element satisfying xy equals alpha y times X for all y in your von Neumann algebra, then X is necessarily 0. And this is the definition that was originally introduced by Kalman when he introduced properly outer. Only he didn't call it that, he called it freely acting instead. But just as a little bit of a brief description here, your intuition should be that if X was a unitary, or even some unitary on a corner, that's saying that alpha is acting inner, or at least inner on a corner. And properly outer says that can never happen. So that's why we're saying X is 0. Although this is a little more general since we're not assuming at all that X is a unitary or anything of the sort. But it is still if and only if. And just as a little bit of a side note, the double commutant under the GNS representation is a pretty well understood object. So as a few examples, if you start with any commutative C-star algebra C of X, and you start with any trace on it, which is just a fancy measure, call it mu, then what we get is L infinity of X with respect to mu. Start with any reduced group C-star algebra, and you take the canonical trace, well, double commutant is just going to give you the GNS, or sorry, the group von Neumann algebra. And there's a lot of C-star algebras with unique trace. For example, any UHF algebra. And a lot of these, when you take double commutant under the GNS representation, you're going to get the hyperfinite 2-1 factor. But anyways, as I mentioned before, the double commutant under the GNS representation is the appropriate object that we should replace the G-injective envelope with if we want to characterize traces. So let's just take a leap of faith and redefine pseudo-expectation. So we'll say that a pseudo-expectation is a map from the universal cross product to the double commutant that satisfies a few things. It should be G equivariant, should be unital and completely positive, and it should have the property that when you restrict down to A, what you get is the original GNS representation. And as it turns out, these are perfect for characterizing traces because, well, pseudo-expectations are in bijection with tracial extensions given a fixed tau. And moreover, there's a more convenient thing that these are in bijection with to work with, and that is elements xt indexed by t and g contained in your double commutant that satisfy a few different properties. So xe should be 1. This is this freely acting condition from before, just applied to every individual xt. It should have a certain conjugation property, and it should have a certain positive definiteness property. So given any finite subset of G, if I consider the finite matrix indexed by elements of F, where the S comma T entry is given by the element X ST inverse, well then this matrix should actually be a positive matrix in the end. Okay, so how do we actually link all of these sets together? Well, going from 1 to 2 is fairly straightforward. Given any pseudo expectation, I can just let xt be the pseudo expectation evaluated at the element t, or rather the unitary ut. And going from 2 to 3, well, given any such collection of xt's, it's actually possible to write down a trace which is given by the following. So evaluated at the element aut, it's the trace evaluated at viewing A in the double commutant times xt. And really, I'm lying a little bit here when I say tau, because I should really be saying the extension of tau to the GNS von Neumann algebra. Okay, so what's something we can deduce from this? Well, given any fixed G-invariant trace, it has unique tracial extension to the universal cross product if and only if whenever xt are as before. So again, xe is 1, you have this freely acting condition, you have this conjugation condition, and you have this positivity condition. So you have unique tracial extension if and only if whenever you have such elements, they are all necessarily 0, except of course for the trivial group element. But in particular, notice that property 2 right here is just the condition that was used in freely acting / properly outerness for actions. So if the action of G on the double commutant is properly outer, then this automatically just forces all of these xt's, of course, except for the trivial one, to be 0. So therefore, we automatically get unique tracial extension, not just to the reduced cross product, but to the universal one, which is a little bit stronger. Okay, can we get something that's a little bit more convenient to work with though? And the answer is yes. So going back to the freely acting condition 2 here, the way Kalman showed that it was equivalent to not acting inner on any corner is saying, okay, assume you did, then you take polar decomposition and prove what you can prove. So I'm going to let xt be some partial isometry ut times the absolute value of xt. And I'm going to let pt be the domain projection of your partial isometry. And all we're going to do is we're going to focus on translating the properties that we had for xt into properties that we have for ut. So xe equals 1. I think we can all agree that the partial isometry that you get is again just 1 in the polar decomposition. This freely acting condition, it actually tells you a lot more than you might think at first glance. So it's possible to deduce that ut is not just a partial isometry, but in other words, but ut star ut is equal to ut star, or in other words, the domain and the range projections coincide. So really you could call this a partial unitary in the sense that it's unitary direct sum 0. And moreover, if you consider the corner of your von Neumann algebra corresponding to this projection, well, this projection is central, and the action on this corner is actually inner with respect to ut. So this conjugation condition, you could probably guess what happens with your partial unitaries. Same thing. And this positivity condition, well, nothing nice comes out of it. So I'll just say that these ut are positively compatible if they arise from some xt satisfying this, this, and that. And just to introduce a little bit more terminology, ut, if they satisfy the first three conditions, I'll say that the action is partially almost inner with respect to these partial unitaries. So what's with the terminology here? Well, partial because ut aren't actually unitaries, they're just partial unitaries in general. So unitary direct sum 0. And almost because the map sending t to ut is almost a group homomorphism in the sense that it's non-multiplicative, but it does preserve the identity, it does preserve inverses, and it also does preserve conjugation in the end. So rephrasing our previous observation in terms of these partial unitaries, so any fixed G invariant trace on A is going to have unique tracial extension if and only if the action on the double commutant is not partially almost inner with respect to a non-trivial positively compatible set of unitaries ut. That's a bit of a mouthful. So the next question you might ask is, can you simplify this in certain cases? And the answer is yes. So the first case, which I'll briefly mention, is if G is FC, so every conjugacy class of G is finite, then you can just completely erase the words positively compatible, which are the most annoying to work with, and the if and only if still goes through, no problem. There's also a theorem of Thomson, again back from the 90s, which says that if G is abelian, and again with additional assumptions, and the way he words it is in terms of all traces simultaneously, but all G invariant traces have unique extension if and only if for every trace, extremal trace, or extremal G invariant trace, I should say, the action on the double commutant is properly outer. Unfortunately, this result actually turns out that it's not correct. And I do have a counterexample that I discussed with Thomson a couple of weeks ago, and he kindly agrees that the counterexample is valid. And I will talk about it at the end. But before that, I just want to quickly mention that the result is almost true in the sense that it's not hard to fix. So if G is abelian, then tau will have unique tracial extension. Remember, properly outer is just saying that there's no non-trivial element T, no T invariant central projection, which you can decompose your von Neumann algebra with, and no unitary on this corner such that T is inner on this corner with respect to the unitary. But you also have to add the condition that both this projection and the unitary are actually invariant with respect to all elements of your group, not just T. And as it turns out, in a case that a lot of people care about, which is the case where G is the integers, Thomson's original result is still actually true. So tau G invariant trace on A has unique tracial extension if and only if the action of Z on this on the double commutant is properly outer. So what's the example slash counterexample? So I can't actually take all the credit for this. This goes back at least a few years ago to some notes by N. Christopher Phillips, I think. But if we let A be M2 and G be the Klein-4 group with generators little u and little v, and we're going to let them act on M2 by, well, little u acts by add this matrix over here, and little v acts by add this matrix over here, it's honestly not hard to check that this is a well-defined action on M2. And moreover, the universal cross product is isomorphic to M4. So M2, we can all agree with, has unique trace. Therefore, the cross product, you have unique tracial extension to the cross product. But what exactly goes wrong here? Because we notice that G is acting by inner automorphisms. So there's no way this is a properly outer action. But there's a little bit of a catch, and that's that the action is not inner, in the sense that you don't actually have a group homomorphism from G into the unitary group of M2 that gives this action. You only have a group homomorphism from G into the automorphism group. So these matrices that I listed right here, capital U and capital V, they anti-commute, but their add maps are actually equal. And in fact, because of this, it's again a back of the envelope calculation that if you have any non-trivial element of G and you pick any unitary W that implements this action, then this unitary can never be invariant with respect to all elements of G. So by our previous characterization, we do get unique tracial extension. Anyways, it looks like I'm out of time, so I guess I'll stop there.